Hello, guys. Good evening, all of you. So, welcome to Cheenta. It's your first class. I'm so happy to have you here in the class. If in case you don't know me, my name is Reed Mukherjee, and I'm pursuing my PhD in electrical engineering in IIT. So, the course, has been designed in a way that enhances both of your normal course knowledge and also external knowledge, so that you learn the subject with its, to building foundations. So today is such a class, and I have decided to help you out in the way that it start in the way so that you can learn the story of real analysis. Probably you have not learned this in your college because I have not learned it in my ISI undergrad days. So I have tried my best to to accumulate all the interesting knowledge that can help you know fall in love with the subject. So coming back to what's the plan for today, we will start understanding sets and the sizes of sets. What do you mean by sizes of sets? Like infinite sets. So the basic thing you should understand is the following: that the arithmetic of numbers, like real numbers, like the numbers, is very different, is very distinct from the arithmetic of infinity. So how is infinity defined? Infinity is defined in a very interesting way. Infinity is not a number, but infinity is greater than everything, every single real number. Okay, infinity is an object, is a mathematical object which is greater than every single real number. So, okay, coming back to what we're going to talk about today. The basic idea is the following: that, right, I should say it's the sizes of numbers, sizes of. So, how do you define numbers here? We define numbers as sizes of sets. So, let's say there is a set A, which is a strict subset of B. So, what do I mean by that? Let's say A is 1, 2, 3, and B is 1, 2, 3, 4, 5. So, mod A is defined as, or mod of any set X is defined as, let's say, the number of elements in X, in the set X. Okay. So what do you get from here, guys? You get that number of elements of A is 3, as you can understand, and number of elements of B is 5. So you can clearly see that number of elements in A is less than number of elements in B. Simple, right? Of all of you, I'm sure you have understood this, but this is not the case with infinite sets, or is it? So if I take this set, that, let's say, all natural numbers. So natural numbers are all the integers that is greater than equal to 1. So natural number is a strict subset of the set of integers, right? So is the size of natural numbers less than the size of integers? This is the question. The basic idea is also, you can understand like this: is the size of natural numbers. So you can say natural numbers lies in natural numbers union is a subset of natural numbers union 0. So that means you take the whole numbers. So you take 0, 1, 2, 3, 4. So natural number is a strict subset of natural numbers union 0. So do you think the size of this natural numbers is less than the sizes of this natural numbers union 0? Yes. What do you think, guys? Any idea? The question is again the following: the natural number is a set of positive integers, and natural numbers union 0 is we are adding 0 to the element. So now this is true, right? Natural number is a subset of this natural numbers union 0. So my question is that, is the size of the natural number set is less than the size of the natural number set union 0? What do you think? Any idea? So
Uh, I feel that though the number is not determined here, but since the other set has one element extra than the just the natural number set. So it is less when only.
Yeah. So it's very natural that you can understand this very intuitively that of course natural number set has size less than this. But the interesting point is that that means you can say that infinity is less than because number of elements in natural number set is infinity. So infinity is less than infinity plus one. Is it true? Genethric and others. Anyone can raise his or her hand and can answer. Okay. No. Okay. Shreya says no. Who says no? Who says yes? Anyone? Any ideas? Is infinity more or infinity plus one more? Which one is more?
Both are also infinity only now, so both are undefined.
Okay. Perfect. So therefore, you can understand that there is some confusion. There is some big confusion when you're trying to, you know, understand the sizes of infinite sets. I mean, there is no clear mathematical argument. That's why some people says yes, infinity is equal to infinity plus one. Some people says infinity is equal to infinity plus one. Is less than, some people are saying less than, some people are saying equal to. So therefore, there is no clear mathematical concept as of now to how to compare the sizes of infinite sets, right? So one of our goals should be to understand today that how to compare these infinite sets, how to understand these infinite sets. So that's our first goal. Understand the sizes of infinite sets. Is the motivation clear, guys? Yes or no? If you think it's clear, please write yes in the comment box, in the chat box. If you say no, please raise your hand and ask your doubt. The beauty of thank you. Okay. Great. Super. Thank you for your participation. So therefore, the beauty of this whole concept is that infinity has a different arithmetic because you know that 1 is less than 1 plus 1. But we have still a dichotomy and a confusion regarding whether this is less than or equal to, right? And you can read an interesting article on this, an idea on this. It's called Hilbert's Hotel. There's something called Hilbert's Hotel. You may like it. Okay, so coming to what's the plan for today? The plan for today is to understand the sizes of infinite sets. So can you give an example of an infinite set? Very easy, right? Natural numbers, right? We have seen that. So we will define the sizes of infinite sets in terms of something called bijection. So I have asked you to revise about bijection. Can someone tell me the definition of bijection? Raise your hand if you want to answer. It's okay. You can be wrong. You can be right. It's okay. I will not scold you. I've done many mistakes too. So anyone who wants to share his or her knowledge on bijection? What is a bijection? 1 to 1 and on to. Okay. So 1 to 1 is called injective maps. And on to is called surjective. So in some sense, geometrically, if we have these three elements here, each element is a 1 to 1 output, right? So therefore, and also surjective. So if it covers, if there are numbers like this, if there are numbers like this, extra elements in the codomain set, the range and the domain, if there are extra elements in this range and in range or domain codomain space, then it is called not, it's injective but not surjective because it's not covering all of them. So if it covers all of them, then it's called bijective because you can see it's 1 to 1 and it's covering all of the elements in the range. So what is a bijective function? It's a 1 to 1 function and an onto function. It's a 1 to 1 map. Every element maps to one element, and it's surjective. It's covering all the ranges entirely equal to the codomain set. For example, if f from R to R, if it is a function, then f of x is equal to x is a bijective function. Because why? Why? Because you understand it's 1 to 1. Every element has only one output, but also it's covering the entire real number space. But fx is equal to x square is not neither bijective not 1 to 1, because -1 and 1 both map to 1, and also x square can only take positive values, so does not take negative values. So therefore fx is equal to x square is a non-bijective map, but f is equal to x is a bijective map based on these two sets, right? All of you understood this, yes or no? Just a small revision. Yes or no? Write in the comment box. Okay, thank you. Great. If any point of time you have some doubt, guys, please raise your hand and ask me your doubt. Okay, you're totally okay with it. Okay, so this is bijection. So how do you define it? So one way understand, if you want to compare this set number of elements with this certain number of elements, understand that if there's a bijective relation between these two sets, their number of elements will be same. So we say that mod A is equal to mod B if there are two sets, mod A and mod B, if there exists a bijection between A and B. So that means if there is a so f is a function from A to B and f is bijective, that implies that A, number of elements of A is equal to number of elements of B. All of you understood this definition? This definition is very crucial. So one example to uh, one interesting property is that if f is bijective to G and G is bijective to H, then it implies that f must be bijective to H. Okay, if f is bijective to G and G is bijective to H, that implies that f must be bijective to H because of the inverse property. Like, you understand, this is intuitive, right? All of you understood this basic idea. If f is bijective to G and G is bijective to H, then f must be bijective to H. So you can learn more about this. So therefore, this is very important property. Okay, I hope all of you understood this. Yes or no? Great, super. Thank you for your answers. So now let's take some simple examples. Okay, first example. So this set, natural number set, is bijective to the integer set. Can someone prove it? So this is for what you have to do. To prove that, you have to find a function from natural number set to the integer set, such that, like, and show that it's 1 1 and 1 1 and surjective. Can someone tell me how to do that? How to find a function from natural number set to the integer set, like bijective function? So here is 1 2 3 4. You have to find a bijection too. So prove that they're bijective. That any idea?
We can take two functions and prove that, like, if it has the same image,
Mm-hmm.
so we can prove that both the functions are same only, because so that it is only 1 to 1.
No, but you have to define a very specific map, a very specific function. Like where will x go? How do you define that? So let's say here is 0, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4. So what if we define like this? The first step we go here and then we go here. So this is the first step. And then the next one we go here, and the next one we go here, and the next one we go here, and the next one we go here. So therefore it's a sequential, So how do you define that? Understand. For f of n, so it's going from, so we have to define a function of natural numbers. So this is number one element. This is number two element. This is number three element. See the arrow. This is the dynamics. Okay. So therefore for 0, for 1 it's 0. N equal to 1 it's 0. For n equal to 2 it's 1. For n equal to 3 it's minus 1. For n equal to 4 it's 2. For n equal to 5 it's minus 2. You see this 4 to 5 is minus 2, 2, 3 is 1 minus 1, right? So understand how can you define this. So if you divide by 2, n by 2, right? If you divide n by 2, you see you will get 1. If you divide n by 3, or like 3 by, okay, if you divide 2 by 2, you will get 1. You will get 3 by 2. If you take the integer part of it, it's 1, right? But it's minus. So how can you define it? Understand. It's very simple. You can define it like, I will take this on that side. Now see, you can define it as n by 2, uska box, floor function. Okay. And for odd, it's minus 1 coming, for even it's 1 coming. So minus 1 whole to the power n into box of n by 2. Does it make sense, guys? Or do you want it to want me to explain it once more? You can ask me to explain it once more. So I can say that for n equal to even, let's say for n equal to even, let's say n equal to 2, we get minus 1 whole to the power n, like that's even, that is 1, n by 2. For n equal to odd, we are getting n minus 1 by 2. Does it make sense now? Essentially, this is what I am meaning. For n, we are getting, for n even, let's say 2, we are getting 1. For 4, we are getting 2. For 6, we are getting 3. For 8, we are getting 4. For odd, we are getting, for 1, we are getting, so for odd, see, we are subtracting 1. For 1, we are getting 0. For 3, we are getting, so here it is not this, but it's minus of this. For 3, you're getting minus 1. For 5, you're getting minus 2. That means you're subtracting 1 from the odd number, dividing by 2, and subtracting, like multiplying by minus 1. Does it make sense, guys? This one? Yes or no? This movement, this pattern, does it make sense? All of you? If no, please raise your hand. I will explain it to you and tell me where it's your doubt. It's okay. For n, it's odd. For any even, it's n by 2. For n equal to odd, it's minus n minus 1 by 2. Great. I hope all of you understood. If you have doubts, please raise your hand, okay? Because there are a lot of people. I cannot call out each one of your names now and ask you. It will be hard and waste of time. So if you have doubts, please raise your hand. It's a responsibility. You're an adult, and it's a responsibility to answer. To stand up for yourself and ask your doubts. You have paid your money, so why will you not? So therefore, this is one such example. Another example, let's say, prove that. So therefore, what do we get here? So therefore, we get the natural numbers have the same is bijected to the integers. So what do we get? We get that therefore natural number set is actually have the same number of elements as number of the integer set. The idea is very simple. Since it's infinity, if you can count in some way, that only happens. If you count it in a countable integer type way. Integer means what? 1, 2, you're counting like this. This is 1, this is 2, this is 3, this is 4, this is 5. You're counting like this, right? For natural numbers. For integers, why it's that? Because you can count it in a similar way. You can see you can start with 0, then go to 1, then go to -1, then again go to 2, then go to -2. There's a sequential idea in that. So wherever there's a sequential idea of counting, that is usually, 1 to 1, or that's bijective with the natural numbers. So we will see this coming up in the sequences. A sequence is nothing but a function from the natural number set to the real number set. It will not be bijective, but it will be a 1-to-1 function. Not a 1-to-1, like it will be, not a surjective function here. So one another example is that the set 0, infinity, rather the set real numbers, the entire set of real numbers is equivalent is bijective to 0, infinity open interval. The positive integers, positive numbers. Why? So this will be a bit hard for you, but it's simple. Let's take fx to be, say, to find a function from R to 0, infinity, right? Can you tell me a function which take all real numbers and map into positive numbers? Any one function? You know that. Very easy function.
F of x is equal to x square.
Great. F of x equal to x square. One such function. Any other function? Mod x. Any other function? But understand here, if you do mod x or x square, it's not becoming bijective. Two numbers, -1 go to 1 and 1 go to 1. Any other increasing function, or decreasing function, like just. So what is meant by bijective? Essentially, it's like it's mapping R to R, but no two elements, like no line is cut by, like the function curve is not cutting any single horizontal line more than once. It's like maybe like this, anyone, any function such that, like this, any function that. So this is not bijective because it's not 1-to-1. -1 and 1 both goes to 1. E to the power x, great, very good. So f of x is equal to e to the power x. It takes real numbers to positive numbers, right? And it's bijective because if e to the power x is equal to, how to check 1-to-1? So note, just take fx is equal to fy. If fx is equal to fy implies x is equal to y, that means for all xy, it implies that f is 1-to-1. For bijective, you can check it takes at least one value, and for bijective, you say that for every z there is some x such that fx is equal to z. But that's easy to understand. So you can understand. Therefore, y e to the power x is 1-to-1 because if it is e to fx is equal to fy, that is e to the power x is equal to e to the power y. That means e to the power x minus y is equal to 1. That means there's only one such value of x, z such that e to the power z is equal to 1. That means x minus y is equal to 0. This must be equal to 0 because there's only one such value where e to the power x takes 1. There is s 0. So therefore x is equal to y, and hence s e to the power x is 1-to-1. All of you understood this? Yes or no? Great. Super. Thank you. Great. So now what's your homework is that show that if you take any closed interval a comma b, it's bijective to c comma d for any c and d. One hint is that instead of finding it, you can prove is that a comma b closed interval is bijective to 0, 1 closed interval. And since 0, 1 c comma d closed interval is bijective again by algebraic changes 0, 1, it implies that a comma b is bijective to c comma d. So show this part, then it will be done. Find a function so that fx takes a comma b closed interval to 0, 1. Okay, great. So this is, so we have done bijections examples. Now coming to countable sets. Okay, everything clear till this point of time? Yes or no? So there is a reaction button here. Okay, so there's this reaction. I don't know if you can see it, but I will show one to you. You can do like this. Can you see the reaction button? Instead of typing it down, yeah, you can use that. Okay, for your work. Yeah, Ruksha. Okay, maybe you have done it mistakenly, Ruksha.
Yes, sir.
Okay, great. So everything is clear till this point of time. What we have revised till now, we have done. We have understood an introduction to sizes of infinite sets. We've understood what is a bijection and examples. This is what we have done till now. Now let's go to the next part. So in the next part, what we'll be doing, the next part we will be learning about countable sets. We'll see examples. I'll see uncountable sets too. Let's go ahead. What's a countable set? Countable set is very interesting. It's very simple though. A set A is called countable. You can understand from the name that it's called countable. You can count in some way. If A is bijective to n, that means there exists a function so that f of n, it goes from natural numbers to A, and A is and f is bijective. So the easiest countable set is examples is natural number, because f of x in that case is equal to x. Okay. For z, we have already seen that f of x is equal to you can prove that it's 1 to 1 here, bijective here. Let's check other examples. Let's say even numbers, twice of natural numbers, even numbers. It's nothing but if x is there, then it's twice x. It takes every x 1 to 2, 2 to 4, 4 3 to 6, 4 to 8. It's map every number to its even counterpart by multiply into 2. Okay, so you can see 2x is also integer. It's prime numbers. Unfortunately, for prime numbers, this function doesn't exist. Unfortunately, prime numbers, this function doesn't exist. Okay, like analytical format. That's whole number theory mathematical people are trying to find, right? So how to do for this case where you cannot do a find a function similarly? So we will also show some interesting problem, but I will come to that. So we have got an examples of countable sets, right? Which has a bijection with the natural numbers. In some sense, I've told this means that you can, since it is it's a 1 to 1. So essentially, what you're doing, you're taking f of 1 to be some number, right? F of 2 to be some number. F of 3 to be some number, right? And so essentially you're counting like f of 1 is 1, like you're counting like 1 2 3 4. So essentially it means you can count A, from where you got the name countable set, right? So yeah, so now what's next? So we have got examples of countable set. So now what are uncountable set? Yeah, Prashant.
Sir, what is E here? E.
Is
Sir,
the
you
set of
said
even numbers?
even number, sir. Okay, sir. Thank you.
Yeah, this is prime. My pleasure. So now what are uncountable sets? The sets you cannot count. That means sets which are not countable are uncountable sets. That means you cannot count like 1, 2, 3, 4. You cannot, there's not a sequential format. Okay. So you will see countable sets a very good relationship to sequences. Okay. Great. In sequences, the order matters, but in countable set, the order does not matter. Okay, great. So now it's time for giving you examples. Uncountable sets. And this is where mathematicians struggle, right, to find out uncountable sets. Right. So this is where they struggled. Why? Because it's not easy to find out uncountable sets, right? They are not. It's not really easy to find uncountable sets. It's not really easy to find uncountable sets because essentially it's defined as the inverse of countable. So you have to check whether it's not countable or not. So what did they do? So to solve this problem of uncountability, what they do is very simple. They focused on. This is how they solve problems. They focused on finding more and more examples of uncountable sets, of countable sets. Of C sets. Let's call it C set. C is uncountable. Countable, okay. It will save time. So they focus on finding more and more examples of countable sets, like how we can form. So when we this is called the arithmetic of a countable set. So how they can form? How can you form countable sets from non-countable sets, more countable sets? For example, from natural numbers, we form more countable sets, right? So how do we find that? Like usually. So once we find this more and more, we will get an idea. Okay, this problem may not be countable. This problem may not be uncountable. And by the end of today's lecture, we will learn a way to prove uncountability. Okay, and it's fun. And that was done by Cantor. Okay. So what we'll do, we will check out good numbers that are countable, uncountable. Before that, we'll get to the properties of countable sets. So let's call it the arithmetic or the algebra of countable sets. So I will use this algebra term more and more, and you will see this coming up again and again in my lecture, because the reason is that from higher mathematical points of view, from a higher statistical point, no, not statistical, mathematical points of view, these are all algebras. Okay, you will see this coming up in sequences, series, differentiable functions, continuous functions, limits. You will see this because algebra is nothing but how two variables interact. Okay, so here two variables are countable sets. So how two variables are interacting to give something new. For example, two numbers are interacting with each other, are getting added to give another number. So it's called algebra. The addition is an algebra and or arithmetic, anything. Okay. So these operations are, I'm referring it to as algebra. Okay. So it's algebra of sets, you will see. Algebra of functions, you will see. All of things they are there in literature when you read books. So I'm explaining you why it's called so. The algebra of countable sets. It's very simple. One first example. So let's say you have taken natural number set, right? And I've given an example that even number sets positive. So let's say positive even number set is a subset of this natural number set, right? So understand in terms of this, a natural number sets are sets, like countable sets are sets which you can count. So if you have a big set which you can count, of course you can count the subset, right? If you take a smaller subset, right? If there's big set which you can count, like 1, 2, 3, 4, you can count. If you take a smaller subset like this, and go carry on, that will also be countable, right? So the first result that I will show it to you, like I will not prove it, but you can prove, I will upload a reading material, you can learn from there. If A is countable, A and B are countable, that implies, and A is a subset of B, that implies that, sorry, if B is countable, and A is a subset of B, then it implies that A is countable. It's very simple to understand. So the proof goes in like this. Since B is countable, that means every element of B, you can represent it as in some sense B1, B2, like this, right? Since it's countable, like b1 bi is nothing but f of I, because there's a function from natural number set to the b set, right? Bijective function. So every I of natural number or every n of natural number goes to bn in that sense. So you can count in that format, like bn is b1 is the first count and b2 the second count. Okay, so f of n is equal to bn. Okay, so if you take bn, essentially a is countable, subset of a is countable means, like instead of taking b1 you are taking like this set a is defined as, let's say, b3, b5, b17, b19. You're taking a subset of it. Okay, you can usually see, you can count it. So there's a mathematical way of representing, but intuitively you can understand that the first property is that subset property. Subsets of countable sets are countable. Why did you share a jam file, Manik? Anyways, please don't spam the meeting group. It's okay. So the next one is that, okay, all of you understood this, yes or no? Please write yes or no in the comment box, or you can just react if you have understood this. Okay, Girish, Disha, Ami, Janitrika, great, super. If you have doubts, please raise your hand. Great, thank you. Super. So this is the first property. The second property, so example is that, as you can see, any subset of natural number, I mean, like any, you know, z is an integer, right? Integer set. So any subset of integer set is a countable set, right? So you have to prove, like, if even numbers, so any, so therefore you don't have to prove it. Okay, any subset of integer set is a countable set. Okay, so that's the first property. So corollary is prime numbers or prime number set is countable, because we cannot show it like here, right? Like this, we cannot find a specific function, so you can prove it in this way. See how beautiful it is, it turns out to be when you use these algebraic properties, how two sets interact. Okay, the next property. Next property is very interesting. It's called finite cross product. I hope all of you know cross product of two sets, right? If not, please, you know. So I will give an example. Let's say cross product of this 1, 2 is nothing but set of all 1, 3. You take element 1 here and every element here, so you get a pair 2 and 3, 2 and 4. For example, r square is nothing but, the plane is nothing but r cross r. That means you're taking every xy number, every point here from r, here from another r. So every such xy such that x comma y pair such that x and y both belongs to r, that's r square, right? So therefore this is a finite cross product of two sets. All of you understood finite cross product of two sets, guys? Yes or no? Great, super. Thank you for replying. So after getting the finite cross product of two sets, we will say that if A is countable, if A is countable and B is countable, that implies that A cross B is countable. Interesting, right? So essentially, the basic idea is this: if A is countable, that means you can, you can count the numbers like here, like this one. A is countable, you can count it, and here on the x-axis you can also count, and you're taking these points like the cross product of them. Just let me turn off the notification. Similarly here, here is also there. So you hope you understand. This is a cross product, right? This is geometry of cross products. Now the question is that how can you count this? Whether why it's countable? It's simple. You can just do like this. You can start with this, then you can go here. You can see there's a countable idea, right? It's not simple like this. That I hope you understand. Oops. So you can see, you can understand each one of them. I mean, you can of course find a very beautiful mathematical proof of this, but I'm just telling you the idea, basic idea, because taking the mathematical proof will take, it's not necessary for you to know right now in the class because it will take some time, but you can read it in your own leisure. I will give an activity and it goes on. All of you understood this? That you can count, like this is you can define as 1, this is defined as 2. The 7th element. All of you understood this, yes or no? And then you can continue like this. Since it's countable. Yeah, Disha? You have some doubts?
No,
Okay.
sir, I just clicked it mistakenly.
Okay, no worries. So did you understand, guys? Yes or no? All of you? So therefore A cross B is countable. You can count it. That's great. Super. Thank you, Samruddhi and others. You can count it. Yes. Simple. So an application of this is very fun, and it's interesting. Observe that we will prove that therefore rational numbers are countable from this. You can count the rational numbers, but rational numbers are very minute, right? So you may think it's not countable, but actually you can count them. How? It's simple. So observe how is rational number defined? It's P by Q, where P belongs to integers and Q belongs to natural numbers, like unique definition. If you see unique definition, the unique definition, unique. If did you understand? For example, yeah, and yes. Where P and Q are co-prime. Right? So therefore observe that 2 by 4. So if you don't put the co-prime, 2 by 4 is equivalent to 1 by 2. So what we do is that this is the Q definition. So what we do, instead of taking Q, we take a bigger set, that is Q dash, which is equal to P by Q, such that P belongs to Z and Q belongs to natural numbers. But this condition is not there. You can understand that Q actually is equal to Q dash, right? All of you understood this? Like here 2 by 4 and 1 by 2 are different, but same. Here it's not considered. Like we are taking this only here, but here we're taking both. Okay. But understand, therefore this Q set, Q is equal to Q dash, right? But this Q set, the rational number set, is nothing but it's equivalent to two pairs of numbers, P and Q, right? P and Q, where P is an integer and Q is a natural number. So therefore, you can see that every rational number is equivalent to a pair of P and Q, right? You understand? Let's say 2 by 4 is equivalent to, you can write as 2 comma 4. 9 by 17 is equivalent to, you can say 9 by 17, 9 comma 17. So therefore, you can see that Q is equivalent to is same as saying a set of all p comma q such that p belongs to integers, q belongs to natural numbers, and p and q are co-prime. But if you take q dash, the co-prime condition is not there. Did you understand this? Yes or no, guys? Do you understand this definition? Did you understand the idea? It's equivalent to. Yes or no? Please reply or react. Super. So therefore understand the number of elements of q therefore will be equal to this set. So what is this set? So therefore let's count the q dash number of elements. So therefore you can understand that q dash, let's call q dash s and q dash s dash. So q dash qs, this set, qs, this set is nothing but a subset of q dash dash, right? Because there is an extra condition here, p and q are co-prime, which is not there. So therefore qs is a smaller set, contains smaller number of elements. For example, here you have only 1 by 2, but here we have both 2 by 4 and 1 by 2. So this is a bigger set, but both remain the same here. Now observe what is q dash s. Can someone tell me what is q dash s in terms of cross product? Can anyone tell me? I just defined this. Can anyone say what is q dash s in terms of cross product? Anyone? It's pairs, right? So what two pairs are there? Very good. Z cross n. Thank you, Preeti. Thank you, Hemant. It's nothing but Z cross n. Because you're taking every pair of Z and n and we are taking it, clubbing it together to form a pair, right? Every pair corresponding to one rational number. So all of you, thank you, Hemant and Preeti. So all of you understood this? Yes or no? Please give it a like for Hemant and Preeti if you have understood this. Very good. Super. So therefore, what we have understood, that Z cross n is therefore so Z is also countable and n is also countable, and therefore Z qs dash is countable. So qs dash is countable, and since qs, the set of rational numbers, qs is a subset of qs dash, and this is a one-to-one relationship with q, and this is a one-to-one relationship with q dash. So since it's a subset, it implies that qs is also countable because subsets of countable sets are countable, and therefore it implies that q is also countable. Did you understand, guys? Yes or no? Whether q is countable or not, this result? Yes? No? Maybe? Great. Thank you, Preeti, Aditi, Ami, Hemant, Disha, Rahul, all of you. Superb. Thank you, Prashant, Girish. Nice. So therefore, we have got that q is countable. So we have got two interesting properties of q, of countable sets. Now what's next? The final idea is countable union. So you can show finite cross products is also countable. Countable union of countable sets is countable. It's a bit hard to understand. Countable union of countable sets is countable. That means if you have a countable set, that means you have a set A1, A2, a countable set. That means you can count the number of sets. These are countable sets. And each AI is countable. A1, A2, all of these are individually countable. Countable number of sets. Each AI is countable. Each AI is countable and number of elements is countable, right? So this union, like A1 union A2 dot dot dot, this union is also countable, right? So let's forget this union, countable union. Let's understand the finite union, A union B. A union B is countable. Very simple. If you take two countable sets, let's say you can count it, the countable sets, right? That's it. That's the A set countable means A1, A2, dot dot this set, union B1, B2, that this set, right? You're taking the countable, right? So, and when you combine this, there will be some common elements. So if you picture it, here's some countable elements here. That's it. You can count it. And you have some countable elements here. These are common countable elements, okay? Now observe, you can count it now, right? Let's say you start from here. So I have taken finite, but there can be infinite also, like you can count it, right? You can count it like this, step by step. I'm taking this. This is a very important idea, okay? This is called dynamical system. It's a movement over time. And you will see in your probability code, this is something related to called Brownian motion. This is the motion of a particle. This was discovered by Einstein and Wiener process, Wiener. The motion of a small particle. So if you know you have full pollen, like not full, I mean flower pollens, right? So if you take a flower pollen and if you put it on any such any liquid with a good surface tension, you will see it will move around like this, and the path it will form, it's called Brownian motion. Okay, it's something called dynamical systems, stochastic dynamical systems. It's fun, it's interesting. This was discovered by Einstein, Wiener. And read about this. Yeah, I just drew the diagram, so you can see the union of two sets can be formed, made into a countable. That similarly you can do it till countable union, not uncountable union. Okay. All of you understood this? Yes or no? I mean, I'm not telling the mathematical proof. I'm telling you the intuition of it. Okay, not telling you the mathematical proof. I'm telling the intuition of it. You can find the mathematical proofs in the PDF I will give you after the class. So we have these three main properties: subsets property, cross product property, and union property. Right. So the next topic. So this is the second part of the lecture. The next part of the lecture is understanding. So let's revise what we have done till now. So we have done, so till this point of time, we have done this. Now we have done uncountable sets, countable sets, uncountable sets, and properties of countable set. Because with the properties of countable sets, we will understand what is a countable set, what is not a countable set. Okay, what is a countable set? Right? From there, we'll understand what is not a countable set. Okay, this is what we have done till now. What's our next plan? Our next plan is to do decimal numbers and decimal numbers and real numbers and finding an uncountable set. Okay, so that's the next part of the lecture, third last part. So coming to decimal numbers, so understand, we will be discussing this next day also. What is the whole idea of numbers? What is the whole idea? How did numbers come? I was telling you that human beings have 10 fingers. Okay, so from that the decimal idea came, the decimal number system came, MStat. They're using 10 10 symbols, 0 to 10 symbols to understand numbers 1, 2, 3, 4 like that. Okay, so therefore everything is based on decimal system. 10 symbols, 10 integers are used to find and represent any number possible they have found out in the history. They used it while farming, they used it while buying food for their children, whatever they could use in the old days, in the before Christ period. So now, how is a real number defined, like using decimal numbers? How is a real number defined using decimal number? Very simple. So I should say uniquely defined. Can someone tell me what is 0.99999999? What is this number? Can someone tell me? Continued 9. What is the meaning of this? Can someone tell me? How can you 1? Why is it 1? It's recurring, yeah. Why is it 1, Vaishnavi? How can you prove it's 1? What is the meaning of this? If you say 0.A1, A1 is a digit, A2, A3, continuous, right? What is the meaning of this? Yeah, so how do you write it mathematically? Let's say A1 is like, A1 is an integer between 0 and 1, 0 and 9. A2 is integer. So how do you write this, represent it mathematically? What does it mean? What does 0.1 mean? It means, so we are going from the very basic of school, okay? 1 by 10, great. What does 0.01 means? 1 by 10 square, right? So what is this? You can see this is nothing but 0 plus A1 times 1 by 10 plus A2 times 1 by 10 square plus A3 times 1 by 10 cube. So therefore you can write it as summation of AI by 10 to the power I from 1 to infinity. All of you agree with this, guys? This is very important. This is what you have done in your class 7, 8. Probably you have forgotten, but this is what is very important to understand. Did you understand this? All of you? Very good. So therefore, you will see now that, so therefore what is 0.999? Can someone calculate? This is called as what sum? What sum this is called? This is called what sum? This one. It's nothing but summation of I from 1 to infinity. 9 by 10. 9 to the 9 times summation. So what is this sum called? Geometric sum. Very good. Very. So can you calculate this? Please calculate this and tell me the answer. Okay, it's 0 to the power. Yeah. Can you calculate me? Tell me the answer. It's 1, right? Why? It's 1 by 10 times 1 by, it's a starting number. So it's a plus a r plus a to the power r square, a r square plus r. This is nothing but a by 1 minus r, right? Can do this geometric sum. So your starting number is 1 by 10, that is a, and its ratio is 1 by 10 also. So it's 1 by 1 minus. This is the r part, this is the a part. This is the constant 9. So you get 9 gets cancelled, 10 gets cancelled, so you get 1. Therefore, this is nothing but 1.00000. This is interesting, right? All of you got this, guys? Did you understand this? Great. What about others? Great, Samruddhi. So now, so you can see that so for example also, you can prove it like 0.27356999999. This continues. Can you tell me what this will number be? Can someone tell me what this number will be? 999 continues. Can someone tell me what this number will be? Very good, Anant. 2757. This 699 continues to be 57. Very good. So that's changing. So essentially, every number has, so therefore this, there is no unique representation as of now. So if we take in decimal system. So the next natural question that comes to the mind is that how to make it unique. So, so the basic idea is to add some restrictions, some basic simple restrictions. How to do that? Simple. How to do that? Any idea? Any idea? So what we will do is that we will just don't allow 000 afterwards. That's it, right? Will not allow 000 afterwards. So what we will do is that just add that it's an infinite sequence which doesn't have zeros eventually. That's it. Which doesn't have zeros eventually. Simple. So 0.717234. This is not the decimal representation. We decimal represent it as, for uniqueness, 0.7233999999. This is the decimal representation, and it's unique. So we'll take one of the definitions like this. Okay. So therefore, understand. So we can prove that any 0 to 1, any numbers between 0 to 1, right, can be represented as a bijection or the connection, like 1-to-1 bijective connection with the decimal representation. That I should say. Non-terminating, that is not terminating to zeros, decimal expansion. For example, 0.314 like sequence. Now, this non-terminating decimal expansions has a bijection with infinite sequence of integers. Now, which type of integers? Belonging to 0 to 1.9. For example, you can see that 3145151999999. This has a connection with 3, 1, 1, 5, 9, 9, 9. This continues. The infinite sequence of integers between 0 and 9. This is very important. It's a bijection. Did you understand this, guys? Yes or no? Did you understand this? Yeah, Ruksha.
No, sir, by mistake.
Okay, no worries. All of you understood this is a one-to-one bijective connection. So instead of writing like this, yeah, Anushka. Okay, maybe I mistake. So we can write it by as 31451519999 as this format, in this format, right? So this is interesting. This is the first step. So how to make it unique? We have found out the solution by making it non-terminating. Great. So with this arsenal of ideas in our mind, what we'll do is we'll march ahead to understand something, and it's very interesting. So we'll show that the set of all real numbers is that x is between 0 and 1. That means this is uncountable. And the proof is very elegant. Just one step. Just understand and just immerse yourself into this beautiful mathematical proof. It's very elegant, okay? Very clever, very elegant, and you will love it. Very simple. So we do a method of contradiction. So we assume that it's countable and we show a contradiction, right? So let's assume that um, this set is countable. That means there is a function from natural number to this set, right? So you can actually find numbers like f1, f2, f3, f4, f5, like this. Goes ahead, and they have a decimal expansion, unique non-terminating decimal expansion, right? Let's say 0.1235976 dot 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 0.315762 dot dot 3 0.11354 dot 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 0.4146362 then 0.515678999 dot dot. Okay. So what we do is that from this set of numbers we find another interesting number. So what we do? So we take the first element out here, the second element out here, the third element out here, and the third one, the fourth element out here. I mean, you understand there is some probably. To make it visually appealing. Yeah, Janitrika?
Can you please tell me how you define this function once, please? The network was not proper. That's why I couldn't hear you properly.
Sure. So we assume that this is countable, this set is countable, okay, Janitrika and others. So that means there is a function, bijective function from natural numbers, bijective function from natural numbers to this 0, 1, right? It's a bijective connection, bijective function. So if it's a bijective function from natural number 0, 1, so therefore 1 goes to this, let's assume that 1 goes to this number, okay? Let's assume that that 2 goes to this number, 0.315 number, right? 3 goes to this number, 4 goes to this number, 5 goes to this number. Does it make sense? Janitrika and others?
Yes, yes.
So now what to do? We find a new number. What we do is that, let's call it 9. So what we do is that, so we found a new number. That means we take 0.1. The first element that you have got, we change it to add 1 to it. 2 plus 1. The second number, we place it in the second place. Let's say it's 2 again. We add 1 to it again. The third number, we again placing in the third place. We add 1 to it again. The fourth number, we're adding 1 to 4 again. We're adding 1 to it again. This number, oh, I'm sorry, I gave the wrong colors. Blue, red, purple. So now what do we do for 9? We cannot add 1 to it. What we do is that we add 1, so it becomes 10. So we go to 0. Okay. So 9 goes to 0. Everything gets added to 1 because 9 goes to 10 and 10 goes to 0 in the fifth place. And for whatever we have got in this sequence, we define a new number like this. All of you understood this definition, guys? Yeah? Did you understand? Yes or no? Yeah, Preeti? Yes, some doubts, Preeti, or it was a mistake? Okay. I am assuming it's my mistake. Okay, no worries. So define a number like this, right? So now what we will do is the following. Now this number, this is also a real number between 0 and 1. Now this number, this interesting number is some function because it's a natural, it's a bijective one. So there is some like natural number n naught such that this number is equal to this number. This is the second argument. Did you understand this? So this number, since it's a bijective function, countable set, so for some integer, let's say 1, 3, 7, 9, 9, 7, 8, that integer is this by the definition, by the assumption, right? Or let's take it, or you can also, it can be 17th also, f of 17, just one such number, unique number, right? Now the contradiction comes here. So how it is defined? Contradiction comes here. For this number, how is defined? So let's take it this, let's assume it's 17. F of 17 is equal to this. That means if it continues like this, at the 17th position, what will you have? So what we are doing at the 17th position, what will happen? We're taking f of 17 and we are changing the 17th number, 17 decimal point to plus 1. Let's say the 17 decimal point is 3. So that means, now understand this f of 17 is this number only, right? So what we are saying, the f of 17 is this number only, and also we are saying at f of 17th position, this number has that position number plus 1. You understand? That means if f of 17 is 3 hai, by if f of 17 में यहाँ पर 3 है, if in f of 17 there is 3 here, then what we are doing, we are adding 1 to it by the definition of this argument, by the definition of the formation. So essentially, by forming this, it's a 4 by the definition how it's formed. So we are assuming that, let's say this number is countable, like this set is countable, so there is a number, let's say 17 on n, for which this number is equal to that corresponding f of 17 is equal to this number because it's countable and it's bijective. F is bijective, and now we are assuming it's bijective. But the way we are defining this function is that at 17th position, this new number is defined in such a way, at 17th position, if it's 3 in the actual number, we add it to give 4. Therefore, this is a discrepancy. That means this f of 70, this number has both 3 and 4 in its position, which cannot be possible, right? Hence, it's a contradiction. Did you understand this, guys? No, yes. Geometry can't. Okay, no, fine. So let's say f of 6 So did you understand the construction? Let's take this. So let's say f of 6. We don't know what is f of 6, right? Let's say how we are defining this function. This new sequence is defined in such a way that, so the new sequence, the new number, let's say the new number is defined as the nth decimal position of the new number is nothing but what? The nth decimal digit of f of n. We are taking the nth decimal digit of f of n. How this is formed? The nth decimal digit of this new number is taken to be the nth decimal digit of f of n. That is for fifth, we are taking the fifth, and we are taking the nth decimal digit, 9, and we are adding plus 1. Okay, if this digit is not, if not 9, if it is 9, we are making it 0. Do you understand this? The new number का nth decimal position is equal to the nth decimal position of fn plus 1 if that number is not 9, and it's 0 if its number is 9. Did you understand, all of you? That's how the new number is defined. Now the basic idea is this, that this new number is actually, we are assuming this real number set is countable. So therefore there is a bijective function of this natural number to this real number, this set. That means this number is staying somewhere in the list of counting somewhere, like when we are counting f1, f2. So there is a number, since it's we are making a fixed number, there's a specific number, let's say 17th or 6th or 19th or kuch bhi, which is mapping to this specific new number, because this number is in this set. So there should be a number which is getting mapped to this number, right? We are calling this number, let's say n0. We took this example 17 here. Now understand, take the 17th position of f17. That's it. Actually, when we are defining like this, it's 3. Okay, let's say it's 3. But the way we are defining this number, it should be 4. There's a discrepancy. Do you understand? Because of the definitions of one, there are two sides. One is the definition, new definition, and the other is the countability mapping argument. This new definition is saying that at 17th position, it should be 3 changes to 4, because 3 is the actual number ka f of 17 ka, 17th position. The 7th position should go to 4, but the countability mapping tells you that this new number should be equal to f of 17. Like there exists some 17 for which this new number is equal to this f of that number. We are assuming that n not to be 17. And this is where the discrepancy comes up. Since f of 17 is that new number, that turns out that by this definition it should be 3, and by this new definition it should be 4 at that point, at 17th position. So therefore this new definition is a valid definition. So therefore, given this is a valid definition, this should be false, because it cannot be both the numbers at the same point. Did you understand? Not Samruddhi, Preeti. And others? Preeti, Rahul, Revant, and others. Please write yes in the comment box. I just want to know. This was the main point. All of you, please say yes if you understood this. Write yes. No, sir. Okay, Prashant, where didn't you understand? Tell me.
Sir, at the point of new definition, can you please repeat from sir new number? Sir,
The new
downwards.
definition tells you that the new
Okay,
number
sir.
is formed, the 17th or any nth decimal position, okay, is defined as, let's say 16th ka decimal position is defined like this. Let's say 16th decimal position, you go to f of 16 ka value, okay. The f of 16 ka take the 16th decimal position. So nth, so this is the basic idea, okay. New number is defined as follows. So the nth decimal position of new number. To find it, what we do is that we go to the nth number mapping. Let's say f of n, and for the error f of n, we are seeing the nth decimal position, and what you are doing, we're adding plus 1 if the number is not 9, if not 9, and we are making it 0, so we are adding 1 if not 9, if 9 we are making it 0. So let's take an example, 17th, let's say 10th, the 10th decimal number position. So what do we do is that, let's say 10th decimal position new number is defined as, we are seeing what f of 10 is going. Let's say that when we are seeing f of 10 is a real number between 0 and 1. So at the 10th decimal position of f of n, of f of 10, what we are getting, let's say 6. So the 10th decimal position of this new number is defined as now 7. Do you understand, Prashant? So we keep on doing like this.
Yes, sir.
It's a complicated definition, but the basic idea is, so why it's done like this, so that this number is not matching with any of the f of i's. That's the basic idea. So we're creating a new number that cannot match with any of this f of I, since every decimal point is changed. Every alternate decimal point is changed. This number cannot be equal to f of 1. Why? Because the first decimal point is changed. This number cannot be equal to f of 2 because the second decimal point is changed. This number cannot be equal to f of 3 because the third decimal point is different of these two numbers, right? Do you understand, all of you? So therefore, the basic idea is that new number cannot be equal to any f of n for any n, since the nth decimal position of f of n is changed, is transformed to get this new number. So therefore, this new number cannot be any f of n, and hence it's a contradiction because we cannot count. Therefore, it's not in the counting. So it's something outside the counting, right? This is the basic idea. Did you get it, all of you? Yes or no? All of you got it? Got the idea? So therefore, what we are getting? So we are getting that the real numbers, because there is a mapping from 0, 1 to 0, infinity. You can prove that. So therefore, we got that real numbers are uncountable. Now you can use mapping from real numbers to other numbers to prove it whether it's uncountable or not. Because if A is bijective B, then a set of A is equal to set of B. Now you can see, therefore, both natural numbers and real numbers are subset. Natural number is a real subset of real numbers. But the size of this is less than the size of this. You can see that, right? The size of this is less than the subset of size of this. So therefore, there is a defined kind of infinity. It's a two different kind of infinity. This is normal infinity. This is another kind of infinity. There is something called continuum hypothesis, which is not proved yet, which says that. But understand, there are a lot of different different infinite sets between this natural numbers and real numbers. Okay, let's say sets like this. Belongs to transcendental numbers, whatever it's that. So we don't know whether this is more than natural numbers, this is less than real numbers, right? So we don't know whether this is this is countable or uncountable. So it's saying that this is the first kind of infinity. This is the second kind of infinity, and the continuum hypothesis says that there is no other infinity in between. There is no other infinity in between. There is a continuum hypothesis. This is very interesting. There is no other infinity in between. So there is a dichotomy between infinity also. Like this is a larger infinity, this is a bigger infinity, this is a smaller infinity. So natural numbers are the smaller infinity, real numbers are larger infinity. So this is what the goal of today's class was, to make you understand the sizes of infinity, how the infinities are formed. And infinity is also a dichotomy. It does not behave like normal real numbers, but this is a dichotomy. This is a different kind of algebra. This kind of, and that's where mathematicians have, and this is called the set theory. That's why set theorists and other mathematicians have dedicated their lives to understanding this. It's very beautiful. It's very beautiful. I will tell you. You can find about the continuum hypothesis. This kind so called undecidable problem. Okay. And God Gödel. This is called Aleph numbers. This is called Beth numbers. Something like. It's very beautiful. You can write like this. So it tells you there is no cardinality. This is strictly between integers and real numbers. Okay. That's the basic stuff. So it's fun. It's not in the syllabus, but I wanted to share it with you because I hope you understand that this is all related. This is how mathematics was developed, and it's my duty as a teacher to make you understand the connections. Okay. So next day, what is our goal? The next day, our goal is to understand the story of real numbers, how real numbers were developed, and we'll see that from the story how limit concept came into being, because we think the limit suddenly came down from above, like apple fell on the head of Newton. Doesn't work like that. Limit came as a logical pursuit. There's a very specific story behind that. Okay, it's not Newton, but there's a very mathematical and step-by-step logical story. And yesterday I explained it to one of my chemistry students. She understood it. Okay, not students, chemistry friends. She understood it. Okay, the story. So it's so beautiful. I'm so happy, I can share this with you, and I'm looking forward to see you in the next class, probably on Saturday, 7 p.m. And we'll really learning about the story of real numbers, right? Thank you guys, and I will see you soon in the next Saturday. This week, it's a guest, special lectures class, so we'll not be doing. So it's not on the usual timing. From next week, it will be Monday, Thursday, and Friday. The classes will be there. So after Saturday class, which I will again take the class on Monday, and then other two classes will be taken by other faculty. So thank you guys, and we'll see you in the next class. I hope you enjoyed. If you have enjoyed, please write boom in the comment box. That's how we interact with the students. So yeah, that's what our methodology. BMM. You should write it down in the chat box if you like the lecture. If not, you can leave. Thank you guys. Thank you, all of you. Thank you. Thank you for your support. Thank you for giving the opportunity to share my knowledge to you. Bye bye.